The name of this channel is Some Assembly Required. Well, this video will require some assembly. You have been warned. I've recently added multitasking support to Saros. This means the OS now supports threads, interrupting a running process to begin executing another and, no less importantly, then coming back to it later, resuming exactly where we left off. This video is about how this piece of magic happens. Let's spoil the whole video by giving away the point. This interruption, called a context switch, is done by saving the processor's state to memory and then restoring it. That's it. If you understood how to do that, you can skip the rest of the video. The processor state is what makes the CPU know what it's doing now and what it needs to be doing next. What this entails exactly changes from one processor to the next, but for the RISC-V, the current state is stored in 32 general-purpose registers called X0 through X31, and one dedicated register for where we're executing called Program Counter or PC. On the 32-bit variant of the CPU, all of those are 32-bit. So to save the registers, the first thing we need to do is create a struct with room for all of them. We'll call the struct context, and it'll have the 32 registers and the PC. Except if we do that, we're storing too much. Let me explain. First, there's X0. While it has a name suggesting it's a general purpose register, and by design and intention it is encoded in the assembly and also in the machine language as if it's just another register, it's actually special. Reading from it will always return all bits clear, i.e. 0, and writes to it are always ignored. This register is therefore also called 0. But since this register never changes, we need spend neither the memory nor the CPU cycles on saving it. We can remove it from the context. Now, X0 is the only special general purpose register as far as the CPU is concerned. All other registers are completely interchangeable. But just because they are completely interchangeable as far as the CPU is concerned, doesn't mean we don't differentiate between them. In particular, we have a convention called Application Binary Interface, or ABI, that gives special meaning to specific registers. Well, this is just a convention. It is a convention followed by many. In particular, it is a convention our compiler follows. As such, we can rely on the meaning assigned to registers by the ABI when we evaluate the register's purpose and importance. For example, register X3 is named GP or global pointer by the ABI. It is marked as unallocatable. This means that the compiler never produces code that assigns values to this register. Its precise meaning was covered by the previous video, now appearing at the corner of the screen. What this means for us is that we can initialize it once at the start of the program and it will never change value again. But if it will never change value, there's no need to save it. We are creating the context struct to store the CPU's state in memory. But once we've performed this store, we need some way to know the address of the context. One way to achieve that is to have a register dedicated to keeping this value. At first glance, this seems like a crazy way to go about it. Sacrificing a general purpose register just to keep track of this struct is quite wasteful. It turns out, however, that there are other values this can track as well. In particular, thread local variables are very similar in that they are different for each thread, and we need an easy way to reference them. As such, the ABI has dedicated X4, which it named TP for thread pointer, for precisely this purpose. Like GP, the compiler will never generate code to write to this register. Without going into the details, there's a way to locate the thread local variables at a constant offset from this register. So all we need to do in order to have a constant pointer to our context is to store the relevant value into X4 while switching into a new context, and it'll stay there for when it's time to switch out of that context. But now, if we're using X4 to locate our context struct, there's no sense in storing it inside the struct. If we can find the context, we know what value needs to go to X4. So with the holes defined, we have our context. The only thing left to do is give the registers a better name. The ABI assigns a name to each register, and those speak to the purpose they carry out, which makes it better and clearer to make changes to them. In particular, RA is the return address. When we jump to a function, the CPU will store there the address to which we need to return. SP is the stack pointer. It is used to keep track of the thread stack. A0 through A7 are argument registers. When we call a function, we pass the first argument in A0, the second in A1, and so on. T0 through T6 are temporary registers. A function can change them without worrying about how that affects the calling function. Conversely, S0 through S11 are the saved registers. A function can store a value there, knowing that any function it calls will either not touch them or save their value and restore it before returning. And with those renames, we finally have our context. Which brings us to context switching. This is done with two functions. SwitchIn takes a context pointer and loads it into the CPU's active state, thus resuming execution in it. In what I know will shock you to no end to know, the function that does the opposite, stores the active CPU state into the context, is called switchout. Let's begin with switchIn though. By necessity, the switch functions are implemented in assembly. They are, however, called from C++ code. There are a couple of things we need to do in order to make that actually work. First, C++ asks that all functions be declared before they're actually called. So here is the declaration. There are two things to notice here. First, the function is declared as extern C. There are a few subtle ABI differences between a C function and a C++ function. While we certainly could make this a C++ function, it's simpler for all involved to just use the C ABI and let the C++ code know that that's the ABI it needs to use. There's one place I use the C++ ABI, and I'll let you be the judge of whether that was worth it. The other thing to note is the noReturn attribute. SwitchIn replaces the CPU state on entry with a completely different one. As far as the original context is concerned, the call to switchIn never returns. Now, it's not necessary to let the compiler know that that's the case, but the optimizations the compiler does when it does know that's the case are quite powerful, so it's quite useful to do so. With the declaration out of the way, let's look at the actual implementation. As I've said before, the A registers are used to pass arguments. We've declared switchIn to accept a pointer to the destination context, and the ABI tells us that the compiler will pass us this pointer in register x10, aka A0. As we've seen before, we actually need this pointer in register x4, aka TP. So the first thing we do is copy it there. At this point, we simply begin loading all of the registers from their respective locations in the context struct. So we're loading RA from offset 0, SP from offset 4, and so on for all of the registers, until our CPU state is identical to what it was when we saved it to the context struct to begin with. There are a couple of oddities, as I'm sure you've noticed. The first is that I start off by referencing A0 as the context pointer, but at some point switch to using TP. Now, since the first thing we did was to copy A0 to TP, you'd expect this to not matter, and in a way you'd be right, except in a way you'd also be wrong. We tend to think of processor instructions as linear, executing one after the other. For pipeline-based architectures, however, so most modern CPUs, that's simply not the case. Our move instruction that copies A0 to TP begins executing. It will take several cycles to completely execute, with the value actually written to register TP at the end of cycle 5, called writeback. A naive implementation, however, would mean that the following instruction, the load of T2, would require this value at the beginning of its cycle 3, ALU. It needs this value in order to add, in this case hex value 72, to calculate the address so it can fetch it from memory at its cycle 4 and write it to T2 at its cycle 5. But the beginning of cycle 3 for the load instruction is the beginning of cycle 4 for the move instruction. if the value will only be available at the end of cycle 5, we're 2 cycles too early. There is some leeway for CPU implementers about how to solve this. When the RISC concept was first visualized, the idea was to have the value actually be unavailable. That thankfully did not last, and on most modern RISC platforms, the code executed is identical to the naive reading of the code. But there's still a problem here, and it still needs to be solved. One solution is to create short circuits inside the CPU's implementation. This means the correct values are made available to later commands even before they were written to the registers. This requires logic, and as regular viewers of this channel know, I opted for the minimal RISC-V implementation I could. So yeah, that's not what we're doing here. The other method of solving this is to introduce something called a pipeline bubble. With this, the load instruction is delayed for 2 cycles until the value is available in the register. Needless to say, that is not optimal. My, and any decent optimizer's solution to this, is to use the value from elsewhere. In particular, since I know the value is also in the A0 register, I use it from there until I'm certain that addressing TP won't introduce delays. Just in case you're wondering, yes, this means writing good assembly code for modern CPUs is significantly more complicated than it used to be. And yes, it was done on purpose. By exposing aspects of the internal CPU architecture to the machine language, the architecture as a whole can be faster. The reasoning was that most code is written by compilers anyway, which means that it doesn't really matter how complicated writing good assembly is. What this does mean is that if, in the 80s, if you wanted your program to run quickly, you wrote it in assembly. These days, if you want your program to be fast, you write it in C, C++, Rust, or another high-level language. The compiler will almost always do a better job than you do if you directly wrote assembly. This discussion does bring forward a different question, though. Before, I said that we're storing the current CPU state in the context struct. But now it seems current CPU state is not a very clear concept. If you stop to think about it, which pipeline stage should we take the state from? And what should happen to the instructions that began executing before that stage and never completed? I won't go into this solution here. Suffice it to say that there is a solution and that we can treat the registers as the state of the CPU. The second oddity you may have noticed about the switchIn function has to do with the PC. In particular, we load it early, but we don't load it into the PC. We load it into register T2. Here's the thing about the PC register. Unlike the rest of them, the PC's value has an intrinsic meaning. In particular, it tells the CPU where to execute code from. As such, the moment we restore the PC's value, we're no longer executing our switchIn function. We're executing whatever it was that the thread was doing before the context switch. Which means that loading the PC has to be the very last thing we do in switchIn. We can only recover the PC after all other state registers have been loaded with their correct values. Which sounds kind of trivial at first, until we look at the addressing modes available and realize that there is no command to do an indirect jump directly from memory. In other words, there is no command to load a value directly from memory into the PC. Under normal circumstances, that wouldn't be too much of a problem. We can load a value from memory to an X register, and we do have a command to jump to a value stored in a register. But these are not normal circumstances. At the point of the switch, we need to account for the value of each and every X register. All general-purpose registers must be precisely initialized. We don't have any we can spare for the jump address. The solution is to use a register that is not a general-purpose one. You see, aside from the general-purpose X registers, the RISC-V also has registers specialized for specific purposes. These are called control and status registers, henceforth referred to as CSRs. And in our case, we're going to be using the MEPC CSR. Let's break that down. The RISC-V has several execution modes designed to allow layered privilege levels. The highest level, which is also the only one our particular CPU implements, is called machine. Since many of the CSRs repeat across multiple privilege levels, they are also often prefixed with the letter identifying the level they serve. So the M in MEPC refers to the fact that this is the machine version of the register. And yes, on a fully implemented RISC-V, so not ours, there's also a SEPC CSR for the supervisor mode and a UEPC CSR for the user mode. The EPC part stands for Exception Program Counter. This register automatically receives the address of the program counter when a jump to the exception vector is triggered. And in order to facilitate the ability to return from exceptions, there is a command to load the value currently stored in the MEPC back into the PC. This command is called mret. And yes, there are also sret and uret. So our context restoration procedure for the program counter is to take the desired PC we want to restore context to, write it to the MEPC CSR, and then finish our switch-in procedure by performing mret. This has the added benefit of also re-enabling interrupts, but that's a subject for another video. What you'll notice, however, is that the commands to do this are scattered throughout the function. We load the PC into T2 as the second instruction of the function, we load T2 into MEPC a little further down from there, and we only execute mret at the end of the function, obviously. That's done for the same reason we use A0 at the beginning of the function. We want to give the new PC value time to settle in T2 before we request it from there, and the same for MEPC. Now, this does mean that operations that are a logical continuation of one another are scattered throughout the function. If you don't like that, well, don't write in assembly. There is a reason this channel is called Some Assembly Required and not All Things Assembly! With that, let's look at switch out. Except we have two of those. The reason we have two of those is because there are two events that can trigger a context switch. The first is a deliberate decision made by the thread. If we look at my sample serial echo thread, for example, it performs a blocking read from the serial port. This means it only has anything to do if there are serial characters waiting. If there aren't, the thread does not need the CPU and will give it up voluntarily. The other way a context switch might happen is through an external event arriving. This might be a timer expiring, saying that some condition has changed simply because of the passage of time, but it can also be an actual external event. Example of those can be an SPI or a USB transaction finishing, data arriving on the serial port, or the 8-bit side of our system requiring something from us. These events arrive in the form of an interrupt. Check out the link at the corner of the screen or in the description for more details about those. A context switch as a result of an external event is called preemption. Saros is a preemptive operating system, which means it allows preemption. There are also non-preemptive OSs, where the only way for a thread to lose the CPU is because it asked to. Those are also referred to as cooperative multitasking. The thing is, our switch out procedure for the interrupt case and for the cooperative case are very different, which means that we have two switch out functions. Let's begin with the interrupt case, which, somewhat surprisingly, is easier to understand. We set the CPU's trap handler address to our switchOutIrq function. This means this is the first thing the CPU does when a trap happens. The first thing we need to do there is save everything. We have no idea where the CPU was when the interrupt happened or what it was doing, so we need to make sure everything is precisely the same when we finally give it back control. Every single register is important, so for the most part, this function just saves every single register to the context and then jumps to the trap handler. There are two deviations from this simple concept, however. The first, not very surprisingly, has to do with the PC. We cannot grab the exception PC from the actual register because, well, the current PC value points at our switch out code. Kind of obvious, really. Luckily, we have the original PC before the exception happened stored in a register, a special register, a CSR, dedicated for precisely this purpose. In other words, we get the PC value from MEPC. A bit anticlimactic, I know. So we read it into T1 and then store it into hex offset 74 in the context struct. The other thing of note is that we're also loading two state registers with values. We're loading RA with 0 and we're loading SP with the value of the mscratch CSR. I've talked about mscratch CSR in the video about interrupts. In a nutshell, it's a CSR we can use for whatever we want. In this case, we store in it the top of the exception stack. By loading it into the SP, which is the stack pointer, we assure that the exception handler runs in a separate context than the code that was running when the exception was generated. We're loading RA, or return address, with 0 for precisely the same reason. We want the exception handling to start a brand new call chain. And by having RA contain 0, we're marking this as the top of the stack. Think of it as an exception context, if you will. The exception context starts here. There is just one more interesting thing to note. When switchOutIrq finishes, it jumps to the trap handler function. This jump, rather than jump and link, means RA isn't updated to point back. Trap handler cannot return to us. In fact, trap handler cannot return at all. This is called a tail call. I'll explain more about it in just a bit. Trap handler not being able to return may seem like a problem, but if we go to the definition of trap handler, we can see it is not. The C++ code marks trap handler with the no return attribute. This means that the compiler knows that trap handler is not allowed to return and will enforce it if needed. If the function does attempt to return, this will result in a compilation warning. We also see that trap handler is defined as extern C, which is why we could call it using its simple name from assembly. Which leaves us one more function to look at, switchOutCoop. For the most part, switchOutCoop looks very similar to switchOutIrq, in that it is going over registers and storing them in the context struct. There are, however, a few differences, and those are very notable. The most notable difference is that the function is considerably shorter. We're not saving all of the registers, not even close. The reason for that difference has to do with the context of the switch. Excuse the pun. SwitchOutIrq was called by the CPU. The execution has no idea control went there and cannot prepare for it. As such, we have to treat everything as important. The only exceptions are registers we know never change, ever, such as GP and TP. SwitchOutCoop, on the other hand, is called like a regular function. The ABI defines what one function calling another can expect. In particular, it only defines certain registers as callee saved, and we only really have to preserve them. So essentially, only the S registers and the stack pointer are saved. The astute viewers will certainly have noticed, however, that we are also saving RA, despite showing up in the ABI as not callee saved. This apparent contradiction is solved if you notice that while we're indeed saving it, we are not saving it into the RA member of the context struct. No, we're saving it into hex offset 74, the member called PC. Okay, I'll freely admit that this is a bit confusing. By saving RA, return address, into the member we designate as PC, program counter, we're fooling switchIn, when it's finally called, to load the wrong value into the program counter. We're effectively copying RA to the program counter, or put another way, we're jumping to where the RA register is pointing. So let's write that explicitly. The JR opcode stands for jump to register. So JRRA opcode would mean jump to the address that register RA holds. And now let's compile this and then disassemble. We can see that the source command is clearly listed the way we wrote it, but when the disassembler looks at the resulting machine language opcode, it interprets it not as a jump register RA, but as a RET. As far as the disassembler is concerned, we put there the opcode to return from a subroutine. Which makes sense. After all, that's what RA stands for, return address. So by saving the RA register in the context at the place dedicated for the PC, we're ensuring that switchIn, when we get to it, will resume executing at the place whoever called us expects execution to resume. That's why, despite the function tail calling a C++ function marked no return, switchOutCoop itself is not marked no return. Which brings us to the tail call itself. Tail call is a term describing the case where one function ends by calling another function. In particular, it describes an optimization where, instead of a standard function call to the tail function and then returning whatever that function returns, the function replaces its own frame with that of the tail function, effectively replacing itself with that function. In RISC-V assembly, this is indicated by using a jump, marked as J, instead of a jump and link, marked as JAL. So we're tail calling the function underscore ZN5 SAROS 6K. What? What is this meaningless jumble of characters? The function we're actually calling is called reschedule, and it is a static function in the scheduler class inside the kernel namespace, which resides inside the Saros namespace. And all of that information, as well as the fact it receives no arguments, is encoded into the symbol name. If you squint just right, you may even recognize those words in there. The mess the result looks like is the reason this process is called name mangling. I won't go into the details of the what and why of the C++ name mangling. I will point out that my most popular Stack Overflow answer handles precisely this, so if you want more info, check the description of the video for a link. I will also point out that there is a tool called C++Filt where if you feed it the mangled name, it will spew back the demangled complete name. And that unintelligible mess of characters is the price we pay for not marking it extern C, thus committing to the C++ ABI. Now, context switching on its own is useless without deciding which thread to switch to, as well as when. The component that handles that is called a scheduler. This video, however, has been long enough as it is. Let me know in the comments if you wish to know more about that as well. Until next time, thank you for watching.